Welcome back to the next concept of circular permutations. All along for the past 5 concepts, we have been talking about permutations of distinct, not distinct objects with replacement, without replacement, or in the context of a row. So the first thing that I'm going to be going through with you is what's the difference between permutations in a row and a circular permutation. And then afterwards, we'll run through how do we actually count the total number of permutations for objects in a circle and the formula associated with it. Okay, so let's say I have A, B, C, right? This is position 1, position 2, position 3, right? This is in a row, right? But let's say I have a circle now. So imagine a circle over here. And then let's say this is position 1, position 2, and position 3, right? Let's just say my 3 slots are here, 1, 2, and 3. Now, I can also put A, B, and C over here, right? And then this will be in a circle. However, when it comes to things being in a circle, right, there's also, there needs to be some sort of a sensitivity whenever we arrange something in a circle. And why is that so? Because a circle can rotate, right? So since a circle can rotate, that means we end up with situations like this, right? Let's say this over here is A, B, C, right? But then we also can end up with a situation whereby it's something like B, C, and A. Now, on paper, it seems like these two are different, but in reality, these two over here are actually the same. And why are they the same? Because you can see that over here, when I write it this way, right, you can see that A is on the left of B, right? And then you also can see that C is on the right of B. So you can see this is the left of B, and this over here is the right of B. And then same thing over here, right? If I write it this way, right, you can see that A is also on the left of B, and then C is on the right of B, right? So these two permutations, number 1 and number 2, they are exactly the same. 1 and 2 are the same because the relative, so here the keyword is relative. The relative positions of the alphabets are the same, are still the same, right? So whenever it comes to circular permutations, because of the fact that things in a circle can be rotated, we need to be a little bit more cautious about how we actually calculate the total number of possible permutations. And the trick to actually calculating this would be to do this. Okay, so the trick or the way, okay, I don't put the word trick, I put the word way. So the way to calculate, right, would be number 1, to fix a spot. Okay, so the first method is to, or rather the first step is to fix a spot. So for instance, let's say I have A, B, and C, right? My first one would be to, in a circle over here, would be to fix this spot. So fix this spot, okay, with one alphabet. So by fixing this one spot with one alphabet, right, this over here becomes my reference point. When I fix this one spot with this one alphabet, everything else, okay, I'm just going to write here, so that everything else now takes reference from it, right? In order for us to work around this problem of circular permutations being able to rotate, we fix one item at a singular spot so that everything else will be slotted in with respect to that one item, right? So with that said, when we fix this one alphabet with this one spot over here, so after we are done with this first step over here, right, as a result, we are now left with 2 alphabets. right? It doesn't matter whether we choose A, B, or C to be the reference point. It doesn't matter. We just know that we need to fix that one spot with one alphabet. After we fix that one spot with one alphabet, we are left with two. And these two alphabets can go into here or here, right? It can go here or here. Now, these two alphabets, right, given that they are distinct in this case, it can go into here or here. So that means, let's say B is associated with here, right? Let's say B has been chosen to be our reference point. That means my remaining two alphabets of A and C, A can be here, C can be here, right? The relative position to B is that A is on the left of B and C is on the right of B, right? Or it could be the other case whereby C is here and A is here. And this would be different because now C is on the left of B and A is on the right of B. Remember, when it comes to circular permutation, it is all about relative positions to the so-called the fixed point, right? The reference point. So how many permutations are there? So the total, I'm just going to write in a different color. So the total number of permutations, right? Initially, we had 3 alphabets, but then we minus 1 to use that 1 to be the reference point. And then the remaining, there are factorial ways of arranging the remaining, right? So we are left with just 2 factorial ways of arranging the remaining. Because initially we have 3, we take 1 out to be the pivot, we are left with 2, and to arrange the 2 into 2 slots, there are 2 factorial ways. So to generalize this, right, I'm just going to write it here. Generally, for n distinct objects in a circle, right, there are n minus 1 factorial ways to arrange everything. And the reason why it's n minus 1 factorial is because we need to minus the 1 to make it our reference point so that everything else can be arranged around it. And that one thing becomes our reference point. So this is the concept behind circular permutations. Let me know if you have any other questions that you have in the comments. If not, do pause this video over here to attempt this question. And when you're done, please resume back the video. If not, I will jump right into this question over here, right? This one question here. So in A, we have, or rather, the context is that we have 2 boys and 4 girls, right? And we can assume that they are all distinct, right? Because it's 2 boys and 4 girls. And we know that in biology, it's practically impossible for 2 boys and 4 girls to be identical, right? So we can label them as a boy 1, boy 2, girl 1, girl 2, girl 3, girl 3, and girl 4. They're all distinct, sorry, they're all distinct. So how many ways can we arrange them such that there are no restrictions? So no restrictions means that I have 6 people, right? 6 people, and I want to arrange them in a circle because this is around a table. So that means for A over here, right, the idea behind it is that in a circular table, I will fix one of them as the reference point, right? Which means that I have 1, 2, 3, 4, 5 slots left, right? So the total number of ways would be, initially I have 6 people, right? I'm minus 1 away from the group to be the reference point, right? So I'm minus 1 over here. Oops. I'm minus 1 over here to be the reference point so that everything takes reference from that one person. And then the remaining 5, I got 5 slots for the remaining 5. To arrange them, there's 5 factorial ways, right? So over here, there is 5 factorial. And therefore, the answer will be just 5 factorial, which is 120 ways over here. Right, so that is the first answer to the first part. Now, for the next part, how many ways can this be done if the 2 boys must sit next to each other? So this, if you manage to solve it, amazing. If not, this is the idea behind it, right? So the constraint of the question is that the 2 boys must sit next to each other. So the 2 boys must sit next to each other, which means now, instead of viewing it as a case where the 2 boys could be separate, we view them as one group now. Okay, so I'm just going to write this here. We now view them as one group. One group. So which means now for part B, right, we have boy 1, boy 2, girl 1, girl 2, girl 3, girl 4. right? Which means that we have 1, 2, 3, 4, 5. We have 5 distinct groups / people, right? And in a circle like that, right, same thing, we are going to choose 1 to be our reference point. And once we have chosen 1 to be our reference point, it means that we are left with 4 remaining slots, right? Because to begin with, we only have 5 distinct groups over here, right? So the total number of ways so far, right, this is definitely not the final answer, would be initially I have 5 groups, I minus 1 to be the reference point, and then I put a factorial to arrange the remaining 4, right, 4 factorial. But remember that within this group itself, right, within this group, it could be a case of boy 1, boy 2, or boy 2, boy 1, right, within the group itself. So we need to account for that as well. And therefore, within the group itself, we still need to multiply this by a 2 factorial because there are 2 factorial ways of arranging these 2 boys within the group, right? And therefore, with that said, the final answer to this would be 48 over here. All right, so that is the answer to this. Let me know if you've got any other questions in this regard. If not, that's all for the circular permutations mastery question. And that's it. I'll see you in the next video for the next concept.